Are you an undergraduate or you're?
Second year PhD.
Second year PhD, great. Anyone?
And I'm a PhD student from the safety department and working on like safety and safety.
Great. So everybody have PhDs? Great. Sorry.
I was gonna say master's student.
Okay. Yeah, okay. Cool. But graduate student basically, right? Okay.
And we have a bunch of folks online.
Okay. Hi people. So let me start a quick intro to myself. I'm Ding. I grew up in China and did my PhD in Michigan. Over there, I've been working on self-driving cars for about 18 years. In particular, focused on the safety of self-driving cars. And my PhD dissertation is one of the first dissertation on autonomous vehicle safety evaluation. And after that, I help my advisor and I we built the world's first dedicated testing ground for self-driving cars in Michigan called City. And then later on, based on experience, I helped Uber to handle the world's first fatal accident with self-driving 2018 after I joined CMU. And then also I participated in the ISO standard 34505 as a committee representing the United States. And also I work many other areas. This paper was published on Nature Communication about how to basically encode the laws into the self-driving cars. And then this will, once this black box is connected to the truck, it will become like a monitoring system about whether the car is following the laws. And also build a bunch of this testing benchmark for self-driving cars. So that's my connection. So who care about this trustworthiness or AI safety? I think all of them care about the company level. Google DeepMind, trusting, IBM, Microsoft, OpenAI all have some department working on safety. Well, I want to say the AI safety or the model safety is slightly different from physical safety. Well, the model safety is more like ethical and do not answer what to answer, not how to answer. Well, physical safety is a little bit more straightforward. They basically, the robot come to me and take my kneecap. Right? So that's what I'm talking about safety. Well, the U.S. government also care about this. They have the executive order on this one, and to follow that one, we have multiple programs from ASF and the DOE, DOT, and also universities. Many universities have these centers related to safety. For example, Stanford have a Center of AI Safety. The former director was my first PhD student working there, and also there are some NGOs. I'm also working on one program called Safe Street for All. That is a $1.2 million project but dedicated to Pittsburgh to study the streets of Pittsburgh and see how identify the most dangerous street here and how we can modify the infrastructure and also maybe for future deployment of self-driving cars. Will that be also some mechanisms? So that's an ongoing project. So why AI safety and trustworthiness is hard? The answer is high dimensional. Mathematically, you can think about it this way. So because for sensing input is very high dimensional, the hardware, each of the cars, if the robotic arm robots are very different. So the hardware is also very diverse. And also the environment and tasks is also very, very diverse. We can have the same robot that work in a manufacturing plant and versus working in a nursing home. The risk is very different in these two situations, right? Even with the same robot. So the environment and tasks also matters too. So to handle such a high dimensional problem, you need a very high dimensional solution. Therefore, we need this so-called large language models, large foundation models. So in this case, we have vision foundation model, we have language foundation models, we have also word model these days to model the environment. So in this case, we need to understand that the setting of the problem is you have very high dimensional problem, you have a very high dimensional solution. Then how to tell the solution is safe is an extremely hard problem, right? Because the data acquisition is for safety critical events is very costly and even risky. Therefore, as a scientist, we always work in a data insufficient setting. Because you always explore the frontier, you always explore the edge cases. Then the mathematical challenge is data insufficient problem. Well, the past 10 years, this wave of AI always make assumption that the data is sufficient. Whether it's language models or image models, the assumption is the data is sufficient. So this is the reverse of the problem. Data is insufficient. What do you do? Right. So let me give you one example to show, like in this data insufficient problems, the amount of data actually may not really be very critical, but the quality of the data. For example, and also if you do not really you did it wrongly, then you may draw the wrong conclusion. For example, this is the California deal the transportation data. So in California, every self-driving cars to get the license, you have the obligation to report your disengagement. Well, which is just take over from the car. So if you look at this cruise, so this is a miles per disengagement. The higher the better. The higher the less frequent you take over. So if you look at this, the cruise is actually going up every year. That means statistically safer, right? Because you take a longer and longer distance to take over your car, right? However, if you look at another one, Waymo. So from 2019 to 2020, it go up, means better. However, from 2019 to 2020, you go much lower, right? And also you go up a little bit. So if you look at this one compared with the cruise, your conclusion is cruise is much safer than Waymo. Right? But we all know what happened. Cruise basically is gone. Right? So what happened is here is only the statistics you look at here does not really the whole picture. But actually where they drive and how they drive is actually very important. I can deploy a car just driving circling my house for 1 trillion miles without this engagement, right? But that does not really represent the safety of this car. I can also deploy the car in Nebraska, for example. That also can drive very long without disengagement. I think you can see from here to here, Waymo is doing something, right? Disengagement has become much more frequent than before. So it's actually trying to learn all the edge cases proactively. Therefore, you can learn faster and actually make fewer mistakes in the future, right? But if you only circling in a very safer area, you become overconfident, and once you go out of your comfortable zone, then you become much harder. So to deal with the situation. So yeah, so then the key question is how you can quantify and identify the tasks, right? Then compare the difficulty of the tasks. So what I ask my student is go out and find the hardest traffic, most tragic traffic in the world for me, and they found this one. This is really hard because you can see this probably 18 lanes of traffic, right? Without traffic lights, and not only that, you have trucks, cars, pedestrians, bicycle users, 3 wheels, right? So you have all kind of things, and they go in all the kind of directions. So great. Let's study this. Design a car that can drive in this situation. I particularly identify the tasks. Is it hard or is it easy? Right. To me, it's very hard, but how to quantify that? Right. So we did not go. This is Ethiopia. We didn't go Africa. We've just found this video online, so we can download this video and use some at that time some tools to process the data and got the trajectory of the cars. So that's a pre-processing, and then later on we kind of this is called a hierarchy direction processing hidden semi-Markov model. So we use basically unsupervised learning and also you call velocity field Gaussian processes to model the environment, and then use unsupervised learning to identify the particular tasks. So through this analysis, we found actually it's not purely random, because it's purely chaotic that how those people over there learn how to drive. We actually found out about 85% of the time. So there were only about 8 cases. It's a little bit different than what we used to drive, but there are patterns. For example, there are patterns that you're driving through, but there is a cars coming from both of your side. You just get used to it. There are also cases that you're driving and then the other car just comes in front of you, and you just get used to it. Just get practice on that, right? So you have this kind of things. You get stuck over there while cars are driving, in the front and in the rear. So just be aware of these situations. But once you get over those patterns, and you'll be able to conquer about 85%. So I think that's what I mean by how to identify the scenarios. But there is a cost once you have the definition of the scenarios. The cost is, first, potential cost is you may have redundant tasks. For example, in this cases, if I rotate the view by 90 degrees of the angles, maybe if you directly apply statistical analysis, you think this is four different kind of tasks. Because statistically, if you look at the vector, they look very different. If you look at the like representations, they're very different. But if you really treat this 4 to be 4 different tasks, then your data to train this scenario it become much more smaller. The data set, each of them become like a quarter of the whole training set. Then you actually have a risk of overfitting. So first we say grouping tasks in the equivariant space. I think that's something we did at the beginning. And also it's not only transportation, but also manipulation. For example, if I put this can in a different location of the table, it should be also considered as the same task rather than here task 1, task 2, task 3, task 4. Right? Then you need to collect much more data, and you could maybe overfitting to some of them. Another potential risk is the interpolating missing tasks. For example, in this case, this is what I did with Uber. Is they have some they have the normal driving situation, the data. We can also find a lot of crashes data under the DOT dataset. However, the most important and most valuable one are called near misses. But near misses is very, very hard to collect. Number 1, it's very rare. Number 2, there's no record. So how to collect those near misses? So we basically have this tool and do an interpolation between them and kind of gradually have a risky factor. We can gradually see what's the portion these two can mix together. Right? So then we can use this to produce the near misses. And the number 3 is the wrong labels of tasks. So for example, once you have a task, that's your task 1, this is scenario 1, this is scenario 2. However, there's always a risk that this scenario kind of in the middle, or you have some features that can mislead your controller that you have a wrong labeled task. That could be even worse. So what we do is that we, instead of have a binary array that say your task A or task B, we have a distribution among all the tasks. This is like your 70% task A and 30% task B. Therefore, if you switch between task one to another, you can still have adaptivity through this like softening clustering. So this is kind of technology called group distributional robustness. This is defined by us, and there's a whole series behind these ideas. So we kind of set the stage. We have tasks, and we have some treatment deal with the potential issue related tasks, right? And then we can go ahead and do things. But as I said, what if we don't have enough data at the beginning, right? So, and in the extreme case, like this is from here to here, you do have some data. This is from this distribution to the other distribution. You still have a sparse data, you can do the generalization. But what about this kind of situation? By the way, this is not ChatGPT. This is happen really here in Pittsburgh, right? Just like our pitfall is just too big that even bus can fall into that. So one of the Uber drivers told me he was on site when this happened, and he saw they were shooting a movie. So yeah, I mean, if you're an Uber driver, you probably know how to handle this. But what if the self-driving car encounters this kind of situation? What do you do, right? So what we did is like if you know the rule, then you can embed the rule directly into the system, just like what I've described here. And if you have a rule that is changing, for example, what I work on this one is a collaboration with my Chinese colleague about designing a self-driving car for Beijing Winter Olympics. So this lane is dedicated for self-driving cars during this event. And the problem is that the law on this lane changes almost every day. So how the self-driving car can be, without retraining the whole stack, how to adapt to this? So we designed a system that adapt to, you can update your laws without retraining the reinforcement learning. So, I mean, that's based on basically you have a rule and you know the rule is changing. Or you know the rule is changing. What if you do not know the rule? So this is we call crash scenarios or agent. That is, basically you can see this one is in the crash report, national crash report. Basically it's if something bad happened and the police was called, and the police go on site and they draw this kind of figures. And they have tap this kind of things, right? And our goal is to reconstruct this scene such that it can do simulation, really more realistic simulations. Okay, so we call it scene generation. So this is difficult because first of all, this is the natural languages. And even more challenging, which is actually okay today because we have very powerful language models. We can kind of encode this one. But this one is really killing us because, I mean, as a human, we can understand, oh, this car coming here and this car coming here, they have some collisions. But if you directly feed this one to ChatGPT 5, you ask ChatGPT what happened. Even today, like 5.7, right? So, I mean, even the latest model cannot even tell what's happening. And at the beginning, when we worked on this last year, they cannot even tell us like which lane it is. Because you can say this is you need a lot of background knowledge to understand which lane, how many lanes, what does this mean? What does this mean, right? So what does this dash line mean? There's a lot of ambiguities and background knowledge into this. So what I did is like we have first of all, there is not enough data set for this kind of figures. So we have to create a data set ourselves to train our encoder. So what we did is we have this structured models that is a graph model to represent this graphs, and we used this kind of graph to generate a figure like this kind of figure that I just showed. That we have the ground truth, right? So then next we have this kind of, we call it templates. So we have to use these templates to generate lots of this drawing figures. And then from this drawing figure and ground truth, we can train this encoder. And from this encoder, we can give this to the language models and then mingle that together with the languages and fine-tune the whole model. Therefore, we can understand this kind of graphs. So in this case, we call the CrashAgent. We have multiple VLMs that working on the reflect, and also we also need to fine tune it with some agentic flow to identify the scenes. And finally, we even make a small. This one is a simulation environment we made that can generate that kind of like a 2D this kind of figures. And finally, after we do everything, we can generate scenes here and project it into color. So that's kind of like what we did in this work. So some examples. You can see this one is a real examples. I mean, even for me, without the training, this is very hard to identify what's really happening. I need to really come here and read those texts and try to figure out what does this all means, right? And after we fine-tune our model all around, we'll be able to do reconstruction. And also, because we can do reconstruction, we can do variation. We can say, oh, what if? We can say, what if this car drives this slower? What if this drives faster? And finally, have some counterfactual, because it's dynamics between multiple cars. What if the other car, there's two cars here driving these directions? So we can generate a lot of scenarios that does not exist in the data set at the beginning. So yeah, I think this is basically our journey. I want to just summarize in my lab. So we build 3 tools. I think we mainly talk about this unknown today with this language model approach. But we also work on constraint safety. We work on this generalization safety. And currently we are working on the foundation model safety. And then we apply them to driving in the public space, in workspace, manufacturing, healthcare, and household. And basically working around generalization, safety, robustness, fabrication, reasoning, and human centricities. So this is a summary of my lab. So pause here and welcome questions.
Any questions in the room, or online folks can either unmute or type their questions in the chat.
So thank you for the presentation. So I'm not sure if I missed, but how does the multi-agent part play a role in this?
Multi-agent?
I don't know if I misread the topic, but did you use the agent to?
Oh, the agentic flow, you mean?
Yeah, sorry.
Oh, okay. Yeah, that's a great question. So basically, what the agentic flow, basically you have a template, you can call larger models, in sequence, I would say. Sometimes you take back, you roll back and go forward. So I think in this case, we first read these graphs, right? We also reconstruct this with a similar we need to find a similar collisions that we call the retrieval, and then give that to the first VLA. The first VLA is a human crash data set. That's a retrieval part, and from this retrieval, we know what kind of the variances could be, and we generate scenarios. And from this, however, these generated scenarios may not have collision. We won't have collision. So we give it a replay and we see whether it have collision or is that what we want? And come back. So this is fully automated by the agentic flow. So
Okay.
Yeah. Yes.
I have 2 questions. I didn't catch, but with the Olympics road that you mentioned, why are the laws changing every day?
Oh, that's a Beijing Olympic event.
Okay.
Winter Olympic event. So the law change every day because sometimes it's dedicated for a very important VIP. Sometimes it's for trucks. Sometimes it's a clean robot cleaning machines. So I mean that's basically dedicated lane, but with a variance of laws.
Okay, that's cool. Sorry. And then my second question was, I think you showed the video of like all the 18-lane traffic you mentioned, and I was just curious, like if the work that you're doing, does it assume that like all the cars are operating like, what's the word? Like they're not making mistakes as they're like operating. I don't know how to explain that, but like if with the pattern there's like room for the cars themselves external to make mistakes.
So we downloaded this video from YouTube. It's only about like half an hour or so. So through this half an hour, there's no collisions. So we don't have these things. But I think the main takeaway from this experiment is that we can identify patterns in a even very chaotic way. So we also do that in the normal street as well. Yes.
So my name is Chris. Thank you for the presentation. So how does scaling such a project look like in public safety process, right? Approaching a public safety institution.
Yeah.
How do you approach them?
No, we are scaling. We actually study all the 100 intersections in Pittsburgh right now. And we work with the police office in Pittsburgh. So it's scalable. But we cannot scale. We cannot serve the whole world right now. But for Pittsburgh level, a few hundred, few thousands of them, running for a few days is fine.
Are there any regulatory or legal challenges that you could potentially face in such scaling process, or
legal use type of face? To be very careful for that. No, I think we are kind of like providing kind of consulting services. We don't have a legal thing for them. But basically, I think is like we have a lot of record, a lot of them just on papers right now. They're like sleeping assets in distributed in different offices. How to reprocessing them in a modern way, and that's kind of what we are exploring. It's more still a research phase. Right. I'm not really selling services yet.
Great.
Yeah.
Ding, I know we're out of time, so I'm sorry to folks who wrote a question in the chat and folks in the room who still have questions. Ding has to run, so I just want to say thank you for your time today. Thank you everybody for being here. We are going to post the video online at the recording, so we hope you'll email us if you have any additional questions. So thank you everybody.
Thank you.